to talk about deformation twinning today. So this is going to be focused on steel, but a lot of what we're going to talk about today extends across a whole bunch of material systems, because we're not, because of course twinning happens in all crystal systems, not just FCC. And you can start the appendix before I forget. Just pass it back, right? And the reason why I'm sticking deformation twinning in here now is because it's so closely related to martensite, right? And it doesn't make sense to talk about the theory of martensite without first talking about twinning, and it doesn't make sense to talk about twinning to focus only on steel. So we're going to hit a little bit of a broader overview of deformation twinning, and then circle back for martensite. But at first glance, it seems that martensite and twinning are actually fairly unrelated. One happens when you're deforming a crystal as an alternative to slip, and another way of accommodating plastic deformation. And the other happens when you rapidly cool steel, right? And so it doesn't necessarily, at first glance, seem that they should be related at all, other than the fact that the way they happen, the mechanism of their occurrence, and the driving forces are actually quite similar. So you've got a shear that happens, and the primary difference is in twins, this shear happens in such a way that the realignment reproduces the original crystal structure, but you have a new lattice orientation, right? So in twinning, we go from FCC to FCC, BCC to BCC. Our lattice parameter doesn't change, right? We maintain our same crystal structure, whereas in martensite, we have a similar shear, but we also have the change of shape, but we also transform to a new crystal structure, right? And so you can almost think of twinning as like a subset of martensite reactions, right? There's a whole lot of ways you can shear and get a new, cause a coordinated shear in your lattice and get a whole bunch of crystal structures, but there's only, there's some very specific conditions that have to be met for that to not change, right, in twinning. And we also see the changes, the shapes, that resulting shapes of the transformed region that we get are quite similar, right? Martensite laths and twins tend to look alike. This is deformation twinning twin steel. What we see is we get these long lenticular shapes, right? And then if we look at martensite, we also have these elongated lenticular regions. Here, what we see in martensite is we see a whole bunch of variants that have formed, whereas in this TWIP steel, twinning-induced plasticity, it's a type of advanced high-strength steel, and we'll talk about in detail in a little bit, but not in this lecture. We'll introduce it to you in this lecture. Because this is essentially accommodating plastic deformation, we're responding to the stress state. So the twins tend to be of one single variant. But if you look at the morphology of an individual twin and the morphology of an individual martensite lath, they look very similar. And there's some nomenclature you'll see floating around, and I think it's a good analogy, but we don't want to stretch it too far. We can think of both twinning and martensite as being diffusionless transformations. And these are often referred to as military, right? The fastest way to move a large number of people on foot is for them to march, right? That's why marching was invented. It wasn't just for parades. It was the most efficient way to get a huge group of people from point A to point B on their feet, right? And so it's this cooperative, homogeneous movement of many atoms together that results in a change in the crystal. And the individual movements are small. Each atom doesn't necessarily move a long distance relative to its neighbor, right? You can think of a deck of cards, right? If you move each card over a little fractional amount, right? So it's only moved a tiny bit relative to its neighbor, you can still get a large shear, macroscopic shear, out of that deck of cards. By the time you're all done, adding up overall 52 cards, the top one is displaced quite a far different distance from the bottom. And it's this coordination of tiny little bits. Now compare that to a diffusional transformation where each atom is sort of moving individually, right, under some bias, right? So you can think about that as like the March on Washington or some other large political demonstration. You have a huge number of people all moving under the same bias, but they're not moving in a coordinated way. People are meandering back and forth across the street to talk to each other. They're walking at a slow pace. They're singing protest songs. And so that's, while there is a driving force, it's not coordinated. The individual people act, or individual atoms act as sort of stochastic elements under the bias. And so this is sort of a kind of an analogy that we'll keep coming back to. Okay, so deformation twinning. We said there was no change in crystal structure, but we do have a reorientation of the lattice. So one thing I didn't explicitly put in the notes, we're not talking about annealing twins, right? Annealing, right? Those are sigma 3 type boundaries that form as a result of purely thermal forces. As the grains grow, you get lower energy boundaries. Here we're actually talking about deformation twins. So you have no twins and you start to deform it, and then they form and grow as a method of accommodating shear, right? Not as a thermal effects during the initial development of the microstructure. Okay, so the change of the shape is sort of this simple shear, right? We've got atoms, planes of atoms, and this is schematic, right? And then you see we get this sheared region, and it makes almost like a kink in the structure here, right? And so if we assume that this is a single crystal and the twin traverses the entire region, what we have here is one orientation, a different orientation, back to the original orientation, right? And then as we continue to deform, this twin region will grow wider and wider, or a new twin might nucleate somewhere else. All right? But what's important is to sort of realize is we can do this in the schematic simply by twisting these little ellipsoids, right? If we think of the atoms, where the center of mass of that ellipsoid moves, as you just move it a little bit, that's how much each of those individual atoms are displacing, right? The individual atoms are not moving very much, but the effect, right, relative to each other. but the effect is a fairly large kink in overall. So let's take a look at the crystallographic theory here. So here we've got a single crystal, right? And we're going to apply some sort of shearing force to it, right? And we end up with a twin region. And we know that by definition, the way we've defined a twin, as we said, it still has the original structure, crystal structure, and all the original symmetry of the original crystal. So basically, if we think about what has to happen crystallographically, we know that our A, B, and C vectors, our lattice vectors, have to have the same lengths and angular relationships to each other before and after the transformation, right? Right. So that has to happen. So let's look at potential ways that this can occur. So here we have a parallelogram that we've applied a shear to, right? And if we look at planes, so this plane here was vertical, it gets moved over, right? And so it's not vertical anymore, right? Plane D was less than, and it gets moved up. Here, plane C, right? If this angle here is half the shearing distance, half the amount of the angle of the shear, right? It's going to maintain before and after the same angle with this bottom surface, right? Another plane that's going to maintain fixed is this top and bottom of our parallelogram, right? That plane doesn't change angles with respect to our coordinate frame. So we know this stays the same. This now makes an angle. So in a sense, the effect of this shearing for atoms on this plane only is as if we had a mirror plane here, right? But it's only for this one particular plane where that's going to hold in 2D. The same thing holds, same concept holds in 3D. It's just a little bit more to visualize. If we have an arbitrary shear on this region, there's going to be some plane that makes some oblique angle here that's going to make the same angle with our shear surfaces before and after the transformation. Okay. So we have two planes that don't change their shape or their size, right? So the first one was defined by that upper and lower surface, right? This plane contains the shear direction, and we give that a special name. We call it the twinning plane, right? And it is we give it the nomenclature K1, right? Right. So you can think about if we shear like this, again, the card analogy, right? To make that shear happen, we don't have to change any pictures on the face of the cards, right? The card itself doesn't change, right? So if we move it over one sort of atomic spacing with each other, then the local neighborhood that the cards see doesn't change either. So then the second plane is this one that makes an angle, some angle theta, with the twinning plane, so that afterwards it makes the same right? And so this has to meet, right? Here we call this K2 is this plane. Nomenclature, our shear direction is eta 1. Right? That's our shear direction. K2 has to intersect our twin plane K1 at this line here, and this line has to be orthogonal to the plane, to the direction of shear, right? So this plane intersects eta 1 at a right angle, right here, right? And then we have another plane which is orthogonal to both K1 and K2, which we call, this is the plane of shear, right? And the shear direction has to lie in that plane of shear as well. And the intersection of eta 1, or K2, and the plane of shear is our eta 2 direction, right? So that's just the geometry of it, of the notation, right? So the twinning plane is our first undistorted plane. K2 is our second undistorted plane, right? Those two planes are invariant under the twinning transformation. Okay. Yeah.
How does the nucleation plane, how is it decided where it is?
It's just, yeah, basically, it's just the one, it's just after you give it the shear, right? There is going to be some plane that goes for basically a positive angle with it. Now we have a negative angle, right? And all the other planes will actually change the angle they make after the shear. Will change the angle that they make with the twinning plane, right?
And it wouldn't have to deform that original position.
Yeah, we're not talking about anything that's happening during. We're just saying before and after, right? So, okay. So there's three ways that this can occur crystallographically, right? And I'm not going to go through the crystallographic derivation of these and work out all the geometry. It's really boring and tedious. Christian has a very good review paper, Christian and Mahajan, if you're really interested in the crystallographic theory of twinning. I see Alejandro shaking his head because you must have gone through it at some point or looked at it at some point. It's dense. It's 100 pages long, and each page is a struggle. But basically, if the twinning plane is a rational plane. So what do I mean by rational plane? The Miller indices are all integers, right? Right. So remember how we make the Miller indices for a plane? It's 1 over the intercept, right? So that means as long as the intercepts, as long as we can make those, the intercepts, we can find some scaling to make them all integers, right? It could be some odd plane like 101, 115, and 6, right? Something really weird. Doesn't have to be nice and clean, but as long as we can make those integers, right? If we have transformations like in uranium, where we end up with twin planes that are irrational, that gives us a different kind of twin. We have changes that involve like square root of 2 the lattice space. So you can never make that Miller index an integer, right? Okay, so if we have the twin plane is a rational plane, and our a to 2 direction, right? Remember, our a to 2 direction is the line that's made up by the intersection of our second invariant plane and our plane of shear. If this is a rational direction, then we have a twin of the first one, right? Just geometry and definition. If K2, the second invariant plane, is a rational plane, and I lost my eta. Eta 1 is a rational direction. So our shear direction is rational. Then this is what's called a twin of the second kind. And when all 4 are rational, which is the nicest case for most hexagonal metals and FCC metals, we end up with what's called a compound twin. So this is a little bit of abstract crystallography, but let's not worry so much about these. We'll keep these definitions. We won't worry about necessarily where they come from. Let's sort of look at what it means, right? So if we have a twin of the first kind, what it says is that an arbitrary direction in the first invariant plane makes the same angle with the second invariant plane before and after the shear, right? And this is equivalent to a 180-degree rotation about an orthogonal direction to K1, right? So we can basically think of the shear as taking everything that's on the twin plane and just rotate it about the orthogonal direction to that 180 degrees. Right? So this here now moves to here. And that's how the shear for a twin of the first kind is developed. Twins of the second kind tend to be rare in metals. They only happen in low symmetry metals, which means like the actinides and really really heavy elements. They're very common in ceramics and geological materials. So here, this is also equivalent to 180-degree rotation, but it's equivalent to 180-degree rotation about the eta 1 direction, right? So it's 180 degrees about the shearing direction. And so what we end up with is some arbitrary direction in the K2 plane has to make the same angle with the shearing direction before and after the shear, right? And that's the geometry of this, right? And if we look at what happens on the stereographic projection, right, you can see here for the twin of the first kind, right, we have some rational direction that is rotated 180 degrees about the pole on K1. And if we look at on the twins of the second type, we see 180 degrees about the eta 1. And compound twins both are such that both of these operations give the same crystallographic orientation, right? So both of these symmetries have to hold true. Okay, so that's the crystallography. That's the geometry of the transformation. So if we take a look at specifically in FCC, right? So this is the types of twins that are commonly seen in austenitic stainless steels. What we're going to see with TWIP steels right? So the twin plane is the 1-1-1 twinning plane, is the 1-1-1 plane. Our shear direction is 1-1 bar 2, and essentially this twin is equivalent to a 60-degree rotation about the 1-1-1 direction, about the 1-1-1 pole, right? So if we think about it, 120 degrees about 1-1-1 is a symmetry element, right? It takes 120 degrees about this, takes this face up to this face, this cube face up to this, right? A rotation of our lattice that way. So it's half of the symmetry element of the crystal, right? And if you think about the 1-1-1 is the close packed plane, right? So we're essentially just rotating that, right? We've got an atom with 6 neighbors. We're just rotating it by 1 neighbor, right? So that's the geometry of the twinning in. Well, so what does the close packed plane look like, right? You've got an atom surrounded by 6 neighbors, right? If I rotate it 120 degrees or rotate it by 2 neighbors, I'm back to my original position. Here I'm rotating it by 60 degrees or one neighbor, right? And so I'm halfway between my lattice points. So now I basically have I think of 2 cubes stuck together, right, sort of angle. It's like a Rubik's snake. Remember that game? That puzzle? That's exactly what it is, right? Hold on, I gotta. Right, this thing, right? Essentially, a twin is like rotating. These are like the 1-1-1, right? It's that same kind of rotation, right? You go from this long. Now you've got a kink, a bend in your crystal. Not necessarily, because you've got 24. I got to think about that. I don't necessarily know if it's that all lower symmetry are necessarily going to have more variance, right? So that's actually one of the things I put up here. I want you guys to think about. This will be a point to ponder question, is how many variants you have, right, of this, right? How many different orientations you can get by doing 60-degree rotations about 1-1-1, right? And this basically changes the stacking sequence, right? So remember, FCC is ABC, ABC, right? We now end up with a kink here, right? And we have a stacking fault. We go A, B, C, A, C, D. And so since the twinning creates a stacking fault, what is going to be a general property of all systems that undergo deformation twinning? What property is going to depend how easy it is to make this fault? Stacking fault energy, right? So right away we know that we're only going to experience this in materials with low stacking fault. right? Aluminum, high stacking fault. Do we ever see twins? Never, right? But austenitic stainless steel, copper alloys, much lower stacking fault, we can easily generate deformation twins, right? And so when we have this perfect fault, we have these atoms matched perfectly at the interface, right? These atoms haven't changed position, and their neighborhood on this side and their neighborhood on this side are both perfect, right? Together, they're not, right? If you look at the whole thing across the interface. But if you only looked at this side and you only looked at this side, their local neighborhood doesn't change. And so this interface then here is perfectly coherent, and we call this a coherent twin, right? So unfortunately, we can't maintain, right? The system can't maintain perfect coherency, right? Because the twins may start out as a thin, coherent plate, but there's, as we'll see, there's a lot of shear that needs to be accommodated by the neighbors, right? So in a single crystal where you've got nothing, no confinement, right, we can grow these perfectly coherent twins. But in a polycrystal, the twin needs to be, right, this grain is confined by the neighbors, and the deformation needs to be compatible, right? So we have a very complicated stress state. So the twin initially starts out as a very thin, coherent plate, and as they grow, become incoherent. And so if we look here at this picture, here we have a twin boundary AB. This is sort of schematic, but it's very reasonable. AB is coherent. BC, this is still a twin boundary, but this is now an incoherent interface between these regions. So these two lattices still maintain a twinning orientation relationship, but the boundary between them is incoherent. And we need the dislocation structure to accommodate the lattice mismatch due to this incoherency. Right? Yeah, they're generally not full dislocations. They're generally partials, right? And so if we look at this partial, if we move this dislocation this way, we're actually going to be growing the twin into the parent, right? So this is the twin down here. This is the parent. If we move this dislocation this way, and we look at how these bonds are broken and reformed, right? We actually see the movement of these dislocations is how we can grow the twins, right? And so because of this accommodation, we see these lenticular shapes, both for twins, and we'll see them again in martensite. And this is because of the elastic, this minimizes the elastic energy. It minimizes the amount of strain that has to be accommodated in the neighboring grains, right? And these interfaces, whenever you see a curved interface like this, you know there's no way it can be a coherent interface, right? So it has to either be a dislocation structure like this, or we need steps, ledges, right, where we have a little bit of coherent region and incoherent region, much like we saw in ferrite. Right? Okay, so we need a very low stacking fault energy for FCC. Prior to 1957, there were people who said that FCC metals didn't twin, didn't undergo deformation twinning, right? But in 1957, deforming copper at liquid helium temperatures, you got a bunch of twins. Since that time, people have been able to play with alloy compositions, right? And we now have a whole bunch of FCC metals that twin. So two of the most important ones that we'll talk about when we get to advanced high strain steels are TWIP. What we call TWIP steels are twinning induced plasticity steels, and they have a stacking fault energy in the range of less than 40 millijoules per meter squared. Remember, aluminum, this is greater than 200, right? So 5 times less than the stacking fault energy of aluminum. TRIP steel, this is transformation-induced plasticity. So this is where you have actually a martensitic transformation that's driven by the stress in the same way that you have twinning that's driven by the stress. And this is even lower stacking fault energy. Right, and these are high manganese austenitic steels, right? So they're FCC, and they're basically silicon and aluminum with lots of magnesium and a couple other things. So twinning, the fact that twins occur does, right, we're changing the orientation, right? So what are the effects? Where can we get hardening? Or I gave it away, right? The twinning is going to create additional hardening, but what are the mechanisms, right? How are we going to get additional hardening? Right? What's happening to we're creating interfaces, right? And so what's that going to do? What's that? We're disrupting slip planes. Yeah, so you hit the 2 parts, right? We're impeding orientations, right? Or we're impeding dislocations, right? So basically, every time you put in a twin, you're reducing your grain size, right? We've got Hall-Petch effect going on. Then we're changing orientation, right? So we're adding new grains, right? So we have a additional hardening effect that comes from texture, right? So if we think about what's happening step by step, initially we're going to have slip, right? In almost all systems, twinning is harder to activate than the easiest to activate slip system, right? So even in magnesium, which twins, if you look at it, the basal slip is still easier than activating the twin system. So basically, we've got slip happening, right? We get a little bit of work hardening. Now we activate twinning. And in FCC, the slip plane and the twinning plane are both 1-1-1. So that means we're activating twins that are parallel to the slip direction, right? So is that going to add any significant impediment to dislocation motion? Right? Not really, because we're just making a grain boundary parallel with the direction the twin is going, right? The twin's not going to the dislocations are never going to intersect that twin boundary, right? So it doesn't, so at the initial stages of twinning, we see a big change in strain, but no real increase in stress. Okay. What's then going to happen? We continue to work harden. Do we actually, I mean, do we, as deformation continues, is there only one slip system active in a grain? No, right? We have multiple slip systems that are active within a grain because we've got all this geometric confinement and crazy non-local heterogeneous stress states. So we're going to start activating other twin systems as well. Once we start activating other twin systems, now we have twins intersecting at oblique angles, right? So we're really reducing our grain size now, right? So this is going to give us, those twin boundaries become additional impediments to dislocation motion, right? And we start to see a very high work hardening rate increase. Okay? So this is a figure out of the reading, and I've highlighted the word, this is a graph of the reciprocal of work hardening rate, right? So this is 1 over the work hardening rate, which means that a big slope here means low rate of hardening. A small slope here means high rate of hardening, right? So basically here in stage 1, we have only slip. We just have dislocations interacting. We start to have parallel twins. It adds just a little bit of an impediment, very little, right? So our slope only changes a little bit here. At stage 3, now we have intersecting twins. So you can see we see a really high hardening rate. And then once dynamic recovery starts to kick in, right, we see our work hardening rate decrease again. Because here in dynamic recovery, remember our rate of dislocation removal is greater than or balances our rates of dislocation generation, right? So twinning has a very profound effect on the stress strain curve. So there's one figure, right? No, that's not quite, okay. So the last topic for today will be twin nucleation. So this is, again, a controversial area, right? There's disagreements even in our department among, right, how twins nucleate, right? I've done a lot of research in twinning and hexagonal metals, and I'll show just a little bit of that research later. Professor Ghazi Saidi looks at it with atomistic simulations, and the people who do atomistic simulations that I collaborate with and her come up with completely different mechanisms for how twins nucleate things, right? This is something that won't be solved, I don't think, anytime soon. This is a challenging problem. What I want to show here is something called a pull mechanism. And personally, I don't feel that this is how twins nucleate. Maybe in limited cases in BCC metals. But the point of this, the point of me going through this and showing it to you is to show that there are atomistic mechanisms which make sense that can give you twins, right? And explain how twins can grow. And that these mechanisms all involve dislocations, right? So even though twinning is a shear, it still involves, they still have to be mediated by dislocations, right? So that's the main point I want to get across, right? Is that there are mechanisms that can explain this, and now it's just arguments among which mechanism is correct under which circumstances, right? Okay, so the first pull mechanism was developed by Cottrell and Bilby in 1951, And basically, so we have a total dislocation of 1/2, 1, 1, 1 direction. So remember BCC, what are the slip systems? The 1, 1, 0 plane in the 1, 1, in the Burgers vector is 1, 1, 1. So the opposite of FCC, right? So here we have a 1/2, 1, 1, 1 total slip dislocation that then dissociates into a sessile 1, 1, 3, 1, 1, 2. So in between A and B, this total dislocation is dissociated into a mobile dislocation, what we call the twinning dislocation, and the sessile dislocation. And if you carefully go through the geometry of the slip system here, we see that the this 1, 1 bar 1 dislocation spirals around the 1, 1, 2 type plane, right? So we have this pole of a immobile dislocation with a mobile dislocation that's essentially spiraled around it. Okay. So once we have this, the twin can then grow in one of two ways, right? We can either increase the number of spirals, right? Meaning this is further disassociate this way, right? That corresponds to a thickening of the twin. Or the spirals can become longer in extent, and that corresponds to a increase in the length of twin mechanisms, right? Again, pole mechanisms are controversial. They're more complicated mechanisms, and pole mechanisms have been proposed for other crystal structures. Professor Ghazi Saidi theory in magnesium is really nice, right? I don't want to make any disparaging remarks on it because it really is beautiful work. But the key idea here is that the nucleation of the twins has to be a dislocation-mediated process, right? There's other mechanisms that, in my personal theory, so notice that this is basically a twin nucleating in the middle. The pole mechanism is a twin nucleating in the middle of the grain, right? My personal belief is that twins, from experimentally, they operate at grain boundaries, right? So we have grain boundary dislocations and a pile-up behavior. Then the grain boundary dislocations disassociate into partials, twinning partials, which then grow the twins out. So this is a really sort of simplified schematic of what my personal belief of how twins grow, right? So these twinning partials that disassociate from the grain boundary that coalesce to form a twin nucleus. Yeah. Yeah. That's one of my disagreements with pole mechanisms. Is no one's ever been able to satisfactorily explain that. Also keep in mind that the people who have proposed this theory, I also happen to work with at Los Alamos, right? So I interacted with them, so I understand what's going on here much better than I understand what's going on with pole mechanisms, right? The individual, the sort of the atomistic details, right? So there's a lot of proponents of different theories, right? And perhaps we may never actually know what's happening, right? The fact is that in a computer simulation, you can make a twin form for pole mechanisms, right? We can't ever observe the atomistics in the bulk, right? We can force things in a thin foil to happen, but that's not conclusive proof, because in the TEM, you can also force aluminum to twin, right? Which we know never happens in the bulk. So unless we somehow come up with some magic technique to actually characterize atomistic atom positions in a bulk sample, I don't believe we'll ever actually know the true mechanism for this, if it's only one, right? There could be multiple nucleation mechanisms working in a given system, right? So twinning is a three-step process. We have to nucleate the twins, right? And I'm going to say here, the time scale of twin nucleation is uncertain. Then we propagate the twins across the grain, right? And this is what happens at approximately the shear wave velocity in the material, so close to the speed of sound in the material. Then the twins grow, right? And the growth of the twin, the speed that happens, is completely dependent on the loading rate, right? How fast you're deforming your sample, and what the stress is, right? And we will stop there for today. We're going to wrap this up. So what we're going to do Friday is I have just a little bit left on fundamental theory. I want to just show a couple little case studies of some work that I've done in HCP metals to sort of clarify a couple of these concepts. And that'll take maybe 15 minutes at the beginning of the class Friday, and then we'll move on to martensite Friday and Monday. Okay? No quiz Friday, quiz on Monday.